Welcome everyone. Today we are going to do a system design solution for a problem called payment gateway, aka Stripe. I have already seen many solutions on the internet and I was not happy about them, mostly because all of them were missing some crucial details. Therefore, I created my own solution and I will present it today. And before going our usual way of defining functional and non-functional requirements, I think here we need to cover a bit of a domain knowledge about card payments, cross-bank operations, financial systems, stuff like that, because this is very important for satisfying and for defining our requirements, first of all. So what is the core functionality that Stripe actually solves? Let's start with some definitions. So we have merchant who sells goods or services. For our example, let's say I'm the merchant and I'm selling t-shirts. So I'm a merchant, I created some website and I would like to sell some t-shirts. Of course, I'm running some advertisement, whatever, and I'm getting some customers, leads, whatever. So the people who are ready to buy my t-shirts. Both merchant and customer have bank accounts where they store or carry all the money, right? So customer has its own bank, let's call it customer's bank, and merchant has its own bank as well. Let's say they are different for now. The core functionality of the Stripe is to actually move money from the customer's bank account to merchant's bank account, giving a green light for merchant to deliver the goods or services this customer paid for. This is basically it. Stripe is responsible only for this arrow. Now, from the technical perspective, how this can be in principle achievable. If you don't have Stripe, merchant would need to implement its own payment system for the website. It means he needs to acquire a lot of licenses, certificates for card details processing, for integrations with card networks like Mastercard and Visa, for integrations with bank accounts and stuff like that, which is quite painful, expensive, and usually merchant does not want to do that because merchant is the business. He or she just wants to sell their product. The way it works is that customer usually pays with card. So apparently we have some card details or just card, which can be credit or debit card, doesn't matter. Stripe is involving also a card network, which is third party. Example of them could be Mastercard, for example. And what is happening actually? Stripe facilitates the payment operations. So Stripe carries all the card details. Stripe carries all the operations, ensures money will not be lost and stuff like that. Also, it manages communication between banks and card networks. So what is actually happening that whenever customer wants to pay, it fills the card details to Stripe and Stripe initiates the payment process. Which is, so the customer's issuing bank, because this is the bank that issued the card. This is why it's issuing. Stripe communicates the card network of this card. So let's say the card is the Visa, Stripe will communicate to card network called Visa. Then Visa under hood initiates the bank transfer between this bank and that bank. So it basically locks money on the customer's issuing bank and prepares it to be moved to merchant's acquiring bank. But since Stripe also wants to make money out of it, Stripe takes a fee out of every single transaction. So we are involving another bank called Stripe's acquiring bank. So actually what is happening is that Stripe initiates the moving of the funds from the customer's issuing bank through the card network to Stripe's acquiring bank. Then Stripe taking its fee, and after some time it moves the rest of the funds to the merchant's acquiring bank. In this situation, every single party here wins because merchant does not need to invest a lot of money and effort to creating payment system. Customer has much bigger trust to system like Stripe, which is secured, it has certifications, licenses, stuff like that, and it is popular, comparing to some random no-name payment service on the random merchant's website. Then Stripe also wins a lot because Stripe takes a fee. So the more transactions Stripe processes, the more money Stripe gets. I will give you a simple example. So let's say I'm selling t-shirt for $100. Whenever customer wants to pay this $100, it enters card details. Stripe initiates the process, so calls card network. Please move this $100 to my acquiring bank from the customer's issuing bank. Whenever money on my Stripe's acquiring bank, after some time, Stripe deducts fee. Let's say it's 5%, so Stripe leaves 5% for itself, and then it transfers the rest of the money, which is $95, to the merchant's acquiring bank. Everyone happy here. Literally everyone is happy. Now we need a couple of words of how card networks work and why we need to involve them in general. Why Stripe cannot just directly call two banks and transfer money between them. Because customer is paying with card details. It's not account-to-account transfer. That's why we need to involve card network which is able to charge a card. Now how this card network actually works. In simple words, you most probably will never find the actual implementation because actual implementation should be licensed and not every single business can integrate with card networks. But in general, it works in two ways for a bunch of reasons. So it has two endpoints called authorize and called capture. Authorize is actually checks transaction on fraud, logs money on customer's account, prepares the transfer. So whenever you send an authorized request to the card network, it will go to issuing bank and tell this bank, please reserve this $100 so the customer cannot move it. Usually the reserve time, so the time while the money is still locked, is 7 to 9 days. If you don't do anything within these 7 to 9 days, the money would be unlocked automatically. Next endpoint is capture, which actually should have authorization ID, which we obtained through the calling of authorize endpoint. This endpoint works idempotently, so it means you can send 5, 10, dozens of the requests to capture the same authorization ID, and it will only move the money that was locked during this authorization. So if it's 100 that we locked, even if we call 5 times this capture endpoint, only $100 is moved from the issuing bank to acquiring bank. That's it. So the reason behind these two endpoints and not one is first idempotency. Second thing, there is a business justification. Some of the businesses need to capture funds much later actually, but that will be it. This information is needed in order to properly design our own system. So I think it's time to proceed with functional requirements, and I will refer to my own technical article which covers the system design with all the details. So this will be our functional requirements, and then let's go one by one. So first one, merchant is able to register itself and webhook. So webhook is just an endpoint on the merchant side where we can send notifications about the payments. If you ever integrated with Stripe, you know that Stripe can send over 100 of different types of webhooks. Based on that webhooks, you can, for example, initiate delivery process. Next one, customers are able to pay for merchants' goods and services. This functional requirement involves moving funds from the issuing bank, so the customer's card, to acquiring bank, which is our Stripe bank. Merchant receives webhooks about its payment. This is already covered. For that reason, we registered webhook. Merchant is getting money for goods, services on its bank account via payout mechanism. So payout is the process that moves money from Stripe's acquiring bank to merchant's acquiring bank. It does not involve card payments anymore, so we don't need to go through the card network. Instead, we will have just direct integration with merchant's acquiring bank, so its bank should be on our list of available banks. And we're gonna initiate so-called payout process, which just sends bunch of transactions that were performed in scope of this merchant to merchant's account. Of course, we already deducted fee, so we leave some of the money on our account still. Ensure no double charge for the same item of goods service. This is very crucial thing. We should omit situation when we can pay once and get two different goods. This is forbidden. We should get only the thing that we paid for, or as a customer paid for. Also, it should not be the case when customer was charged twice, but actually it receives only one item of the good or service. This is very crucial thing. It is our correctness, and we will take care about this. Last requirement, it comes from the legal perspective because I contacted a bunch of the guys who were working in banking. So actually every single bank and payment gateway as well, they have a legal requirement to have something called ledger, which is storage for the transactions. And this ledger should contain all possible events about what happened in your system, so you can trace back what happened to money and to prove that money in your system does not appear from nowhere and does not disappear to anywhere. Now we should deal with the non-functional requirements. So first of all, of course, we're going to have a lot of traffic. I googled Stripe numbers, and what I came up with is 500 million payment requests per day, which translates to 10k RPS on peaks, requests per second. Around 5 billion ledger events, which is payment related in event. It means one payment might have like 5 to 10 different events that happen. So it was created, it was authorized, captured, failed, refunded, whatever. It translates to around 100k requests per second on peaks. And we're going to have around 2 million merchants. Next thing, which is quite important, is CAP theorem, which is availability versus consistency. Of course, we want to have our system as highly available as possible, but we still need to have some level of consistency. So for this reason, we do have strong consistency, aka linearizability, aka recency guarantee for payment processing. So this is required in order to prevent double charge. We still are good with eventual consistency for merchants related data and ledger data. It means if payment just happened, we don't care if it appears straight away in our ledger data or in one day. The only important thing to us is we don't have data loss. So no data loss allowed for ledger entries. And I think for merchants related data, we can afford data loss because anyway, all the payments and all the money related information will be stored in our payment storage and ledger storage. Merchants data is only for basically visibility, dashboards, whatever else. Next up, we have correctness, which means debit and credit should add up to 0. This is kind of our legal requirement for audit storage. Merchant receives webhook with at least one. Merchant receives webhook with at least once guarantee retry in 30 days. What does it mean? That our merchant can actually have its API down for a day, for 3 days, for 1 week even. And it means that still, if payments happen and we successfully process some payments, we need to deliver this webhook, because if we don't deliver it, merchant would just not initiate delivery process of the goods or services for its customers, and this is kind of critical to business. So we are going to retry webhook sending for 30 days. So if the merchant's API is down for 30 days, okay, we gave up. We are not going to send this notification anymore, so merchant would need to go and manually check every single payment on the dashboard or something like that. We have one more peculiarity about this design, that we might have a seasonal spikes. For example, Black Friday, when every single person might buy more than usually. Okay, now having our functional requirements, let's go ahead and start building something, satisfying them one by one. So merchant is able to register itself and webhook. We can start with something easy and simple one. So we're going to create some API. Of course, we're going to need some storage. So the communication will be simple. We have RESTful API. We have an endpoint called post merchants. It will create data inside our database, which will store all merchant-related information, which can be ID, webhook URL, where we're going to send the notification, bank account details for payout, secrets that we are going to use to sign webhook payload, and also that are going to be used for merchant to directly call our API. On top of that, this storage can include goods and services that merchant is paying, but this is kind of redundant information for our system design. Okay, cool. I think this is good enough. Let's proceed. Now we have customers are able to pay for merchants, goods, services. This requirement is a bit tricky. Let's also consider that we should ensure no double charge straight away, because these two are kind of related. So what we are going to do here, first of all, let's introduce our third-party card network, let's say Mastercard. As I mentioned, it has two endpoints, authorize and capture. Let me draw a bit of the UI so we understand how we're gonna split this on the API endpoints. Usually what is happening, merchant has some screen with goods. Every single good has button pay. When you click this button pay, usually you are getting redirected to the page where you can enter your card details and click final pay button, which actually redirects you already on the bank payment confirmation, which means usually you will be prompted something like fill in one-time code that you received on your mobile application and stuff like that. So this is already something that is happening on the card network domain. It's not happening within our system anymore. We could actually do it as a single endpoint, of course, but due to UI consideration and also due to another reason to omit extra authorizations that we can spawn, because we have this edge case that client might be broken, they might have some broken rollout, or it can be bad network, whatever else. So it can happen that client actually sends two exactly same requests, and if they are landing on the one endpoint called pay, in this case, first thing we're going to do, we're going to create a payment entity in the database, and straight away after that we are going to call authorize endpoint. So we're going to lock the funds on the customer side twice, which is not the end of the world. One of the authorizations are going to be unlocked in 7 days, but why to do that bad user experience? Instead of this, we can create payment entity on this side, and when we are on this screen, we are only ensuring for the same payment we can do authorization only once. And how we are going to do it, I will show you in a few seconds. So I'm introducing a new endpoint called payment. This will create only payment entity. The payment entity contains ID, of course, for idempotency status. So the new one will be with status new. When we authorize, it's going to be with status authorized. The amount of the payment and authorization ID, which initially will be null, because until we authorize, we don't have authorization ID. So this is the endpoint which is called on this stage. Now let's define an endpoint that will be called on this arrow. So whenever we are sending this payment/ID, what we are going to do, we are going to check what is the status of this payment, and we gonna forbid and return, I don't know, 400, whatever else, if the status is not new. But again, if the client is sending this request twice, what can happen is two different threads are going to read the same new status and trigger two authorization requests, which we want to prevent. Therefore, what we can do, we can use actually the well-known pattern called optimistic concurrency with compare and swap mechanism. And for that, in order to prevent double authorization and requests to card network, we are going to introduce another status called authorizing. Now, how it will work with optimistic concurrency? Upon receiving request payment/:ID, we are going to update our status in database in the following way. So take a look at this SQL transaction or SQL statement. We are going to update our payment, set the status only in case if currently status equals to new. We're going to detect whether we actually can proceed with authorization or not through the rows affected result from the database. So if 0 rows were affected, it means the status is not new anymore. So we cannot go because other transaction already switched it to authorizing and proceed with authorization. As simple as that. If you want to add additional SQL things on top of that, meaning you won't have rows affected, you can also put some additional layer or increase the isolation level of your database from read committed to snapshot. And in that case, it will even fail if you try to do this statement. So yeah, two choices. But in this case, since concurrency level will be actually low, so worst case, we can get this parallel request in case of some retries from the client. We should be good with just optimistic concurrency on read committed. So after we updated the status to authorizing, we can go and within the same request proceed with the authorization. Then we receive authorized ID and we change the status to authorized and auth ID to whatever we received from this response. It will be exactly same optimistic concurrency like that. And then after that, let's consider our system simpler. So whenever somebody calls this endpoint, we understand that payment should be completed and finished within the same request. So we don't want to split on two steps, authorization and then capturing. We're going to do everything in once, but still card network is designed in a way that we need to do two requests. So therefore, after updating it to authorized, we are going to issue another request, which is capturing based on the authorization ID. And then after the result from the card network, we're going to update it again here and put state to captured. That's it. We are actually done. And this is how we are going to do it in our Stripe. Card network, then we'll move the funds from the issuing bank to acquiring bank as we discussed before. Again, if we fail at some point and we issue exactly same request again, if we see that the payment is in status authorized, we actually can call capture again because we remember capture is idempotent. So no matter how many times we call it, it will transfer only exactly the amount of funds we authorized before. So we are safe here. Now, merchant should receive webhooks about its payments. So what we can do here, let's define a merchant API, which is very unreliable in principle. And upon every single update to database, we also can issue requests to merchant API on the webhook endpoint, and that will be it. We satisfied our requirement. Merchant is getting money for goods/services on its bank account via payout mechanism. So how this is going to be working is we're going to have payout service, which can be some background service or whatever. This payout service is going to read from the payment storage, and whenever this payout service sees some captured transactions, it will put it to the batch, and then it will send this batch to bank API, the actual bank API that is ready to transfer the funds to the merchant's account. This thing is external to us as well. And then payout service will just handle the errors and will retrigger it again if, for example, 3 transactions are successful, but 1 captured transaction was failed from the bank, so bank replied that it didn't accept it or something like that. So we're gonna have some, I don't know, retry jobs storage, and we're gonna save all the failed payouts there. So later on, we can actually retry them again up until they are successful. Also, we can sync data about payouts to the merchant's dashboard, so merchant can see like the payment to its account actually failed and he needs to fix, I don't know, some account number in the bank, whatever else. And sure, no double charge, we already handled this one, and audit all transactions are stored in the ledger. So basically, exactly same events that we are sending to merchant API, we are going to send to our audit storage in order to be able to trace every single thing. So what is going to happen? We are going to define another storage called audit storage, and upon updating our payment with new status, we are also sending this status and all payment related information to this storage along with the merchant's API. So these two can be actually parallel. That's actually it. This system is already enough for a couple of users and just a couple of machines. It will work. And now we are going to proceed with non-functional requirements to actually scale it, to add availability and stuff like that. So how do we handle high traffic? Actually, the common practice for handling more traffic than you actually have right now is sharding for storages and replication for computes. So first of all, let's handle the computes. Among them, we have API and payout service. Both of them are actually stateless, so we can just spawn a bunch of their instances, put a load balancer for API, and for this one, we can just spawn more instances, and that will be it. We are actually done. All will be good. Again, this is because they are stateless, and we don't actually need to care any data. So we can lose them arbitrarily and add new instances arbitrarily as well. Now, let's move and proceed with the storages. So first, our storage, let's say, and the main storage is the payment storage. So how do we scale it? I would say the good, let's also add here merchant ID. I think the good key for sharding here would be a payment ID, not merchant ID. Why? Because we might have a very big merchants that gonna be hotspots on our database, on our shards. So for that reason, we are going to shard it based on the payment ID. And this way, we're gonna have really even distribution, and we are not afraid of any spikes due to Black Friday or something like that. The problem here, let me actually outline it. The problem here is that in case we want to get all the payments per merchant ID for merchant dashboard or something like that, we end up with having scatter-gather approach, which means we're gonna query all the shards we have in order to get payments related to merchant ID. And this is not the best thing to do. So in this case, we can use CDC and derived data storage to sync this data to some merchant storage, and then from UI we're going to query directly this merchant storage for the merchant dashboard once seeing how to solve this problem. But we are not aware of any specific actions regarding merchant dashboard. But yeah, the real world example would be that we have another storage for dashboard for sure. Again, for rebalancing, we are going to use consistent or rendezvous hashing, which will ensure very optimized rebalancing in case we want to add new instance or scale down some of the instances. Now audit storage, exactly same scene. So this storage going to handle payment event with payment ID on its own. I don't know, some JSON data, whatever. So I think here we would like to shard by payment ID exactly because most probably in case we even want to query this database, we want to get all the events related to single payment ID. So to trace what happened to this exact payment. So I think this would be a good scene. Otherwise we would need again do scatter gather. So I am noting here shard by payment ID, and again consistent and rendezvous hashing for the rebalancing. Now retry jobs storage. So for this one, I don't know what entity we might have here. I don't know, some job is the ID, status, type. So I think here we can just shard by job ID, and that will be it. Our payout service, what it really needs to do is just to grab some job, retry it, and update the status. So you can basically, it can go to any possible shard it wants. It doesn't really matter. The thing is to make it evenly distributed, so there is no one shard that has a lot of unfinished jobs or stuff like that. Same thing for rebalancing, consistent or rendezvous hashing. Okay, seems like we are going to handle quite a big amount of load right now. So now let's handle availability versus consistency. We would like to be as highly available as possible, of course. We should have a strong consistency, aka linearizability, aka recency guarantee for our payment storage because we want to ensure no double charge, we want to ensure no double authorization transaction issued for card network and stuff like that. We're okay with eventual consistency for merchants related data and ledger data, which is our audit storage, but we should ensure that no data loss is for ledger entries. For merchant storage, I think we can kind of be okay, and merchant related data that we are going to lose it. One point here that you might notice that if we shard it by payment ID, we kind of cannot work with merchant related data anymore because based on payment ID, you don't know where this specific merchant data is located. Therefore, what I propose to do is that we switch it to a different database called merchant storage, and you can sync data here with CDC or by directly writing there. We will get back to it a bit later, how we can manage all of these side effects and write to every single storage based on one operation. But so far, let's also cover sharding. So this one we're gonna shard by merchant ID. Why? Because we actually for this storage we want to find all merchant related information by its ID, and of course it's gonna be merchant ID. If we are using derived data, we can have something like merchant payment, which basically is just simplified version of our payment object ID and stuff like that. This is for dashboard only. Now having all of this, let's basically move how we're gonna ensure high availability. So for computes again, which is payout service and API, they are already replicated. So if one is dying, another one will catch up. So no problem with that. Let's go to our storage. The typical strategy for high availability in the storages is replication. We have many types of replication, and let's maybe start with audit storage. You remember we don't need here a recency guarantee, so no linearizability, but we should prevent data loss. It means that leader follower does not work here because we can lose data on leader elections. So when we write to the master, it didn't replicate to replica, and then master died and leader election chose the replica to be new master. This data forever left on the old master. Still, there is another choice which will ensure no data loss, but also will ensure linearizability, which is RAFT or any consensus algorithm. replication based on it, but this is very expensive. We don't need recency guarantee here, and we don't want to spend too much money on that. Another case would be leader follower, but synchronous replication, which means upon each write, we should still wait until replica is synced. But in this case, we cannot lose replica. If we lose replica, we cannot process any writes, which is also like, it doesn't give us much more availability than it was before. Other choices that I would choose here actually is leader or leaderless. Why then? Because this payment event data, we are not going to have many concurrent requests trying to write to exactly the same payment event, to exactly the same ID, because we only have one event. Yes, we have at least once delivery, which means this event might be tried to be inserted 2 times, which database will handle by the constraint, whatever else. So that's why we can actually easily afford here to be leader or leaderless, because we don't have concurrent updates. Therefore, we cannot lose data with the lost update anomaly. And leader and leaderless are much cheaper than RAFT consensus algorithm. Let's move to merchant storage, and since we agreed we can actually lose data here, because it's just dashboard, right? So in this case, we can definitely say this is leader follower async replication, and this will be enough. Because this is cheap, this is fast, this is pretty effective, but in some small percentages of the cases we can lose data, but that's okay. Now what about the payment storage? This is very interesting one. You remember this one should be linearizable, and in case you hear word linearizable, recency guarantee, strong consistency, there is only one choice, which is called RAFT Paxos, aka consensus algorithm. That's all you can have, and the replication guarantee you have here is that you can lose any amount of replicas until you have majority. So in case you have 3 replicas in the RAFT cluster, you can lose basically only 1, because 2 replicas are majority here. If you lose 2 replicas, the cluster is not operable, you're gonna have downtime. Let's see retry job storage again. This guy has pretty much exactly same requirements as our audit storage, because we don't care about recency guarantee. The only thing we care is that we don't lose the jobs, so we actually retry them within some time. So I will put here leader or leaderless, and that will be it. Unfortunately, we might have the concurrency here, but the thing is that this concurrency is not very harmful. So in case we're gonna retry something twice, it's nothing, because all the jobs should be guaranteed to be working with at least once guarantee, which means there should be the duplication mechanism, so we don't insert some data twice or something like that. And this will be ensured on the bank side with the reconciliation. So we are going to request the transaction record from the bank and check it with our audit storage and check whether there is some inconsistency, whether we missed something or we overdid something, and we will compensate on our side. So this process is actually really required on our side. And the duplication on our side we can ensure via, I don't know, unique constraint and a bunch of other things. So this is leaderless. If you want really no data loss upon concurrency as well, you can put RAFT here as well, but I think it's redundant. All good. I think we actually satisfy this requirement, and now we should be actually highly available. Next up, debit and credit add up to 0. This is kinda ensured through our audit storage, and merchant receives webhook with at least once guarantee retry in 30 days. Actually, you might notice already a small design problem here, because what do we have here? Whenever we write to card network or certain request and we update our payment status, we actually need to update bunch of different things. So first of all, we need to send update to merchant webhook. Second thing, we need to update audit storage. Then we might need to update also merchant storage in case we want to sync the data there, right? So it is one operation result, but 3 side effects. Maybe it will be a fourth one, I don't know, sending notification to some notification system, whatever. The common pattern here is to actually introduce message broker and handle these side effects independently. So what I will do here, I will go ahead, introduce a Kafka, because it will not lose data, it has at least once. I would push this payment event to the Kafka, and I will have a bunch of workers, each worker per side effect. So I will have separate worker or set of workers for updating merchant API. I will have set of workers for updating audit storage, merchant storage, and stuff like that. So this worker is going to write everywhere. Now with the merchant API, introducing this Kafka actually solves a lot of our problems, because before that, since merchant API is very unreliable, this request might be waiting for a very long time, and we don't have that much of a time because we have HTTP timeout on this request, so it will be failed and client will not know what to do. The second thing, we don't want to wait to this merchant API because of we want to write to other storages, we should go ahead and stuff like that. So now, since this is very independent, we can do these side effects independently, and what we need to do is to send requests from API to card network, then update our main payment storage. Everything else is going to be carried through the Kafka. So we just need to ensure we inserted the event here, and everything will be working just fine. Of course, there might be a miss because API can die after it updated payment storage, but before it inserted event to the Kafka. For that, we might have some additional worker that is going to check that every single payment storage has some effect on audit storage, for example, and that's how we don't lose data at all. Since we want to keep trying sending this update to merchant API basically for 30 days, of course, we cannot retry just in memory, because our API will just die and forget about that it needs to retry for the next couple of days, right? So we're also going to use our well-known retry job storage. And if our 3 retries in memory didn't help, we just push it here, and then there will be worker again that is going to read from this job storage, and it will just retry merchant's API, and with the created time and last updated time, we can actually understand that 30 days already passed, and we're going to close the job and forget about webhook update. Of course, we're going to use some exponential backoff because we don't want to overload merchant API, and we don't want to pay extremely lot of amount of money for running our CPU for no reason. One more requirement, since we introduce Kafka, we also make sure that it should be scalable and reliable, aka highly available. So for scalability, we just introduce more partitions for the topic, and for reliability, we can introduce replication for Kafka topics as well. So this should be just fine, no data loss, nothing, it will be okay. And I think that's how we pretty much covered everything. With regards to spikes, actually we are not afraid of them because Kafka will serve as a buffer, so we can easily control how much load we process on all side effects, storages, and recipients basically. The payment storage is sharded based on the payment ID, which is unique and evenly distributed. So if we can handle with all our cluster, I don't know, 10K per second, if we have additional 2-3K per second more, it will not be a drastic overload for some specific shard because it will be evenly distributed between all the shards. So we actually do not care about spikes. We should be just scaled enough so we have, I don't know, some buffer of CPU and RAM, I don't know, maybe 30-40% of buffer, and it will be all right. So I think that's it. Thank you a lot for being with me. You can also follow and read the technical article, which has much better and nicer pictures and maybe deeper and more detailed explanation of decisions made. Please go to the comment section below and actually leave your feedback about the technical decisions that were made here. Don't forget to subscribe to my social media, Instagram, TikTok, Telegram. I'm posting updates there. We are doing system design solutions, POCs, lead code, preparing to interviews, stuff like that. Again, thank you for your attention and see you.